going to work with some more conditional probability here. Still dealing with our deck of cards. We're going to draw one card. Just draw a single card. As we've talked before, we know that the probability of getting a heart is 1 out of 4. We know the probability of getting a red card is half the time. Half the time it'll be red, half the time it'll be black. If we're doing conditional probability, heart given that it's red, if we've been told someone cheated and said she's holding a red card, we know we've narrowed it down to 26. Of those 26 red cards in my hand, I want to know how many of them are hearts. It's only 13 cards in the deck. Sorry, 13 hearts in the deck, which is half the time. Notice that the probability of drawing a heart, given that it was red, and the plain old probability of getting a heart, those guys are not the same. So these guys are not independent, or they're dependent. Why don't we say that? Okay. If we checked them in the other order, we could do the same sort of thing. Okay. If we're told that the card we're holding is a heart, we know that we've narrowed it down to 13 cards. Out of those 13 cards that we're holding, then we say, well, how many of those hearts in the deck are red? And you'd say, well, all 13 of them are red. Okay, so if I cheat and tell you that I'm holding a red card, that narrows it down to I cheat and tell you I'm holding a heart, then by default it has to be red because all of the hearts are red. Okay, and if we compare these two blue probabilities, they are not equal to each other. Okay, so it still tells me this is a dependent situation. I mean, either of those, either the purple pair or the blue pair, I can check. Either one is going to say no. Knowing one of these gives away enough of a clue that it affects the probability of the next. If we go back to our tables that we were looking at in the last last section's videos, okay, where we had freshman and sophomore students, we had male and female students broken down. Up here on the top, we said here is the probability of a male being chosen if I draw one student at random, and the probability of a sophomore being chosen. So maybe I want to find the probability that the student is a male, given that the student was a sophomore. Looking at the table, if I'm told for sure that I'm talking to a sophomore student, notice there are 29 of them altogether, 11 men, 18 women. And so from those 29 sophomores, I can block out this half of the table. Not like literally, but okay. And so then of those, how many of those 29 students are men? We say 11 of them. Notice that the probability of me drawing a male student, knowing that he's a sophomore, is different than me drawing a male student out to begin with. 23 over 60 is not the same as 11 over 29, which means these two events are not independent, okay, or we'll say they're dependent events. All right, so using the table at home, I want you to find me the probability that the student I've drawn is a freshman, given that the student is a female. I want you to find me the probability that the student is a female, given that they are a sophomore. So pause the video, see if you can use the table to get that done, and then decide if these two events are independent or not, and same with those two events right there. So pause the video, see what you can come up with, turn it back on to see if you're right. If we're told that the student is a female, then from the table we are looking at those 37 students. Of those 37 students, 19 of them are freshmen. So 19 over 37. Again, if we narrowed it down to be a sophomore, we've got 29 on the bottom. Of those 29 sophomores, 18 of them are female. Notice that the probability of getting a female student I didn't have on the list yet. So when I want the probability that the student is a female, that's 37 over 60. Since these two probabilities are not the same, the probability of drawing a freshman and a female and a sophomore are dependent events. Okay, same with this pair up here. Probability of a freshman is 31 over 60. We'll move on to another example here in a second. Okay, here's the other table from the last section that we were working on and finding probabilities for. If you would pause the video here in a moment and find these 3 conditional probabilities. And then from those, you'll have to find 3 additional probabilities that aren't necessarily over here and determine whether or not these pairs of events are independent. So pause the video, see what you can do, and then turn it back on to see the answers. All right, so we're not an athlete. There's 61 of them. The ones from Kansas are 20. So given that we're from Kansas is 77. An athlete is 57 of those. Same thing here, not Kansas is 73. 41 of them are non-athletes. Okay. To decide whether or not Kansas and non-athlete are independent or not, we need to know if this probability is the same as that. And since they're not, we say no. Here we need to see if this probability, given that we're from Kansas, is the same as this probability, and it's not. So again, we say no. And here, not an athlete, the probability that it's not an athlete, 61 over 150 is not the same as 41 over 73. Okay, so none of these pairs are independent. Okay, hopefully this gives you a good start on working on those. Next video, we'll pick up, we're going to do some more tree diagrams.